So this is probably good to do before we actually proceed with more of the book. Um, uh, I think it's worth to just do a few, I guess, exploration exercises on pointers. Like exactly how do we get address of a variable? How do we actually modify the contents of memory address by updating the pointers and just kind of get a feel of how to operate with C pointers in general. So I'm going to actually not proceed with the book and just create like an example project again and go from there. So let's see here. So in this case, I don't want any distractions. I'll just kind of do this. Maybe get into like a little focus mode for programming. Yeah, I need to respond. Hmm. My daughter's misbehaving at school, so um, I'll have to talk to her later. Uh, anyway, so what happens when you're a parent. You have other worries in life. Okay. So let's have a project called pointers test, right? And then we'll have dot C, and let's go. All right. So as usual, let's do include stdio.h int main int argc. Then we'll have char star argv as an array, and then we'll return 0. Okay? Now, the first thing we want to do is let's actually tell the difference between percent %p versus percent %d, right? When we print um, a memory address. So, like, remember I had said that uh, pointers are just numbers, right? Because memory addresses are just either 32 or 64-bit. Going forward, I'm just going to say 64-bit numbers in general. There's actually like two ways we can print them out, right? Like the first way is that we can format the printout as like the nice hexadecimal, and the second way is that we can print them as like a normal number, like basically the number to the cubbyhole inside your shelf, right? So um, let's actually declare a variable, right? Int x equals, I don't know, 1337, right? And so basically what we've done, right? If we take a look at Excalidraw, maybe okay, okay. So basically what we've done is given some portion of memory, what we have now done is we actually assign, right, a variable x that has a value of 1337. But what is the address, right? What is x, right? Where does that live in? Well, remember, we can actually get that by doing this, the address of some variable, right? So we can actually print that out, okay? So I'm going to first print it out as what the book would do by using percent %p, right? The address of x is, right? And we'll say percent %p, new line, and then we'll say the address of x. Okay? So remember, ampersand gets the address, right? So we save that, and we actually run our program, right? So we'll do cd, I think it's projects, cd pointers test, we'll do gcc main.c, we'll do a.out, right? So the address, here, let's write that down, right, is, huh? What happened? Oh, it's my little tablet thing. Okay. Okay. So the address, is it because of the tiling thing? Oh, it is. Oh, I need to convert to using a tiling manager. Oh, maybe next time. Okay. So the address is 0x, right? And then it's what, 7? Let's try that again. 0x 7 f f what is it, c9 1, right, c8 d a8 4, right? That's a long number, right? But you think about it, right? When we're looking at bytes, right, if we represent 0 to 255, right, which is basically there are 8 bits to a byte, right? Right? Meaning that we have basically 2 to the 8 combinations from 0 to 255, right? So that's equals 256, right? 0 counts as 1, all the way to 255, that's 256 values, right? Now, it's the case that 2 of these is actually 1 byte, because it's actually 0x002 0x f. If you do the math and convert that to decimal, it's just like something like this, right? Because this is what, I'm gonna embarrass myself. This is 15 times 16 to the 0, and this is 15 times 16 to the 1. So that is like what? What is it? 15, 16, 0, 3, 9, 5, 1, which is like what? 0, 4, 1, 240, and then you have that 1 at the end, which is going to be 15, because 16 to 0 is 1, then we get 255, right? So it's the case that 2 of these are 1 byte. So we count all of this. That's 2, that's 3, that's 4, that's 5, right? That's 6, right? So wait, 1, 2, 3, 4, 5, 6. So this is actually a 6-byte address, right? But really, there's more here, right? 0, 0, that's 7, 0, 0, that's 8. So that's like the address, right? Because 8 bytes, right, is actually 64 bits. Okay? That's cool. I mean, that's a great developer view to have, right? But I want to know what number this actually is. So we can just also print it out as a number, right? Of x as a base 10 number, because the other one was as a base 16 number, right? So we can do something like %d, and we can just get the address of x, right? So that's going to give us a warning, right? And oh, oops, I think it's actually LD, long integer, because D is 32 bits only, I think. Is it L or? I think that's okay. Wait. Print F on long int C. It's LD. Okay, LD. So LD, that's fine. The warning is fine, because they're like, oh, you may not. You're trying to print out like a pointer, but you're printing it out as an integer or like a long integer. Can you check your work? That's fine. It's intentional, because this big number here is actually the base 10 address of this. So if we converted that, right, This is base 16, right? To base 10. We'll get this number, which is the exact same thing as this number, right? 140725672748532. Right? So these two are actually the same. It's just that they're represented in a different way, right? Okay. So we go back to our picture, right? Where we're like, okay, well, in this case, we have memory here, and then we have X 1337. This here is actually cubbyhole 14072572748. That's how much memory we have, right? That's the address. That's the cubbyhole number, right? So that's actually how you would actually reference an address of some variable, right? And just to prove it to you, what does ampersand give us back, right? Yeah, it gives us back a number, right? Although it gives us back a number, say we want to actually save this, right? Do we do long int, a equals %x, right? Do we do that? No, we don't. We don't do that, right? Because why? If we were to declare something as just like a normal number, but we meant to have it as an address, how how would we actually know that's an address and not a number? Right? So that actually doesn't make sense. Instead, we had to declare something as a pointer, right? When we grab the address of this, that actually brings us back a data type. That actually brings us a data type of int star, which is a pointer to an int. So we did this. Let's say int star a equals that. We know that we're holding an address, so we can just do something like this, right? Oops. Right? And yes, we get slightly different numbers, but that's because now we're holding the value at a different address because it's a different run of the program. But really, if you really want to save an address to a variable, you have to declare it as a pointer to that data type, right? Because if we did something like this, and I don't think it's an int, it's like a long int or something, or it is an int, a pointer to an int. Duh. Okay, so because we're not saving the full address itself, right? So now if we did something like this, b equals that, okay, will we actually compile? We would actually compile because they're both technically numbers, right? So we actually printf the number. In this case, right? Too many arguments. Why? Oh, LD. Oops. The number. I think this has to be a long int, given that we're assigning it this way. Maybe. Yeah. So this happens to actually work, right? Because again, they're equivalently numbers. So let me just back up here. Okay. So we know that in order to understand whether or not what we're getting is a number, right, or a memory address, we depend on our declaration here, right? We depend on our declaration. We know that ampersand x is a pointer to an integer, meaning that this here, this number, right, is actually a pointer to some number here. Okay? But again, it's fundamentally just a number, right? It's just the memory address. Okay? So you can easily mistaken yourself by assigning it to a real number type. Long int, just to say that, we're basically we're assigning this number to be a 64-bit integer, right? Because our memory addresses are 64-bit. But when you actually start to operate with it, how can you tell if this big number coming in is just a number or a memory address? So I'm going to reiterate. That's why we declare our types to be a pointer to an int, a pointer to a long integer, a pointer to a character, and so on. So let's just say this. If this was itself a very big number, right? Of course, we can't fit that in 32 bits because that's way bigger than 4 billion. We would have to declare this as long int, right? Now, again, if we were to get the memory address of this, right, what type would we get that? That's still a long int because all memory addresses on our 64-bit computer is going to be a long int. It's going to be 64 bits, right? Now, but when we want to ask, okay, well, I want a pointer to this value here. I want a pointer to this value here. What do? Well, again, I use the ampersand, right? I use ampersand to get the pointer to this integer here, right? And since we've changed it to long int, it's now long int, right? A pointer to a long int. A is a pointer to a long int, right? Now, this is even more consistent now in that both are just going to reflect long integers, right? But again, I've intentionally made this very confusing because if you're not sure actually whether or not this number, right, is actually a memory address or just a regular number, then you're kind of messed up. You're kind of screwed because you could potentially access somewhere entirely different when you meant for it to be just a normal number, right? Or you can treat this normal number, right, as a memory address and go, or you can treat a memory address, whatever, other way around. You're not going to get what you want, right? So again, when you declare the pointer, right, when you want a pointer, when you want to save the address, this declaration has to be whatever type you have declared here, right? Versus all memory addresses are going to just be basically long, right? It's going to be always going to be a pretty big number in this case. The reason why, again, right, we got away with something like this, because indeed, this is actually an integer, right? So that's why we want a pointer to an int. This address here is essentially a pointer to an integer. Okay? So about dereferencing it, right? So now we have A here, right? What happens when we actually want to print out what's in there, right? What's inside A? Okay, well, we can just do print the value inside A is, remember when we do the asterisk, right? When we have a star, we're basically digging in to that location memory. So right now this could be like 5, right? But then now when we have it on this side, because this is the left side, but this is technically the right side, right? The right side, when we're doing star A, we're going to dig in to get that value back, which is going to be 1227, right? If we didn't have this star, we would just get back again a memory address, because now at this point A is a pointer type, right? So without the star, we're reading it as a pointer. We're reading it as a int star rather than an int. The star A turns that back into an integer, right? So let's just see what that prints out. So we'll do gcc main.c. What am I doing? Forgot the formatting again. Jeez. Okay, new line. Okay. Okay, so we do get 1227, right? Again, it's because star A, when we're just operating, that's considered a right side, right? Whereas this is the left side. When you declare a data type with the left side, you're declaring a pointer to whatever data type it is. Okay? Now, prove it to you. What happens if we do this? Int C is A. Is that valid? It is, right? Because we're assigning a pointer type. So this is essentially the int star to another int star. So they're going to be pointing to the same place, right? So if we're thinking about it visually, right? If we have this and we had A, right? Point here. Now we're bringing in C, which actually is assigned to A. Well, technically, it's pointing to the same place, right? And again, no star because this here is a pointer, right? If we starred it like this, that's on the right side. When we're starring on the right side, we're digging into the value. So basically what will end up happening is that we're actually assigning the memory address 1227 in this case to the pointer C, right? We don't want to do that. That's confusing. Instead, we want to assign the address, the address where A is at to, again, a pointer to C, which is going to be the address of C, right? And then what we need to do is we can just print that out again. The address of A is, and we'll even do it as a pointer for properness, right? And we'll say the address at C is, or of C is, so notice that we don't do star again because we're not digging into the value, right? We're just simply referencing the memory address in this case. Because why? Again, right side star means to dig into the value. Left side on a declaration, right? On this declaration means you're using this star as like a way to signify that this is going to be a memory address. So we compile again. Okay, so notice how we got the same memory address, right? This is in line with our diagram here. So again, what do we do if we want to dig into that value? Well, we have two choices now. We can star A or star C because they're pointing to the same place. So let's try that. The value at A is, we'll do this, and the value at C is, we'll do this. Okay? So then we do star A, star C. Okay? Alrighty. Let's see what happens. So, GCC. Typo. Sorry. Today was a work day, so I'm a little bit tired. Okay. Okay. So, warning. Okay, whatever. So, the value at A is 127, and the value at C is 1227, and the value at C is 1227, right? Same, because they're pointing to the same place. All right. Now, what happens if we want to update, right? Okay. Well, we can update can we do this? X is 5 because this is 1227. A, right, is pointing to the address at X, right? So technically, if we updated X is 5, if we dug in to, I mean, obviously we know we did printf, right? We know that X is 5 now, right? But what happens if we dug into A? Oops, at A is now. What happens if we do this? We dug into the value. Remember, A, right? A is a pointer, right? A is a pointer to the address at X. So A is pointing to the address at X. Okay? Star A will get the value at X. okay? And we had updated x's value, right here, a non-pointer variable, to be 5, right? So if we dug into A and even C, let's just say, digging in, right? Star on the right side is digging into that value, digging in for the value. What will we get? Interesting, right? So A is now 5 and C is now 5. Makes sense because why? We had reassigned X, right? We had reassigned X to be 5. It never changed location. A is still pointing. Oh, this is bad. Okay, bad diagram again. I'll just redo things because I'm just not coordinated enough. So we had A, right? Pointing here. We had C pointing here, right? And we had updated X, right? We had updated X to be 5. Didn't change the location. But A is still pointing to the address at X, C is still pointing to the address at X, therefore they should be 5, right? What happens if we did this? Well, okay, since we know that these addresses, right, are pointing to X, right, which has 5, what happens if, let me ask you this. Can we actually update X without touching X? Right? Can we change this value here to be something else without even doing an assignment on X? So remember, there were 3 cases, right, of what star is. On the right side, star means to dig in at the memory address for the value. On the left side, star with the declaration of a data type, like for example, like this, means to actually create a pointer to that type, right? Create a new reference, create a new memory address for that, whatever for that type. But what about the scenario where star is again on the left side, right? But with no declaration, right? That's how we actually update something, right? Based off of this rule here. If we look back in our document, but if star is on the L side without declaration, type declaration, I should edit this. Type declaration such as star z equals 78, it means that we want to modify the value located at the address of z to 78. So this is key to how we can actually update a value without ever touching x, right? We know we have a and c that point to x, right? So what happens if we did this? Or even this, right? What happens? Well, let's see. First, let's concentrate on this line here with the star a equals 78, right? This technically means to update the value pointed by a to be 78, right? Well, what is a pointing to? That's actually x. So let's print it. The value at, right, a is, remember to dig into the value at a, this is star a, right? Because a is a pointer. Now let's also check out what x is now. Okay? And just for kicks, what is c? Remember to dig in the value on the right side, star c, because c is a pointer, right? That's interesting, right? So we have the value of a is 78. We know that because we updated the value pointed by this variable to be 78, right? Because again, star on the left side without type declaration means to update the value pointed by that variable, that pointer, right? So since a points to here, we update that to be 78, right? It makes sense then x becomes 78 and c also becomes 78 because c also points to the same place as a. So we see that here, right? Now we did that for C. We're doing it for C too. And I'm just gonna copy and paste, right? And we'll see what happens. 123. We did this without even touching X. I think that's pretty cool, right? We were able to update places in memory without even touching the original variable. We've done it like through a backdoor way, basically. Okay, I'm gonna leave it here. That's enough, exercises for today. I think I'm gonna do more tomorrow. We're just gonna keep doing it until we feel comfortable, right? So I'm gonna upload this to Git. All right. Oops. Just do maybe that. Okay. And then I'll have time to go through more tomorrow. So thank you for sticking it through. I hope over time my explanations get better. But for now, just watch this video many, many times over because that helps me.